Good morning, everyone. My name is William Arnold, and this is my video presentation on Lab 1 for Physics 2211 on constant velocity. First, I'm very quickly going to go over the methodology for this lab, which includes the setup, measurements, and variables that I used in order to obtain the ultimate conclusion on constant velocity. So first, I'm quickly going to go to Tracker, which will be able to show us the video setup and axes that I chose. So as you can see here, for my object, I chose a cylindrical water bottle that I rolled across a flat lab table. The rolling started prior to the meter stick, so that the object will be able to speed up and reach its constant velocity. And then I started the frame right here at the beginning of the meter stick and ended my frames right here at the end of the meter stick. And I situated my axes so the water bottle rolls right across the x-axis with little variation in the y. And it is also moving to the left here. And I set this up to where moving to the left was negative. So as you can see here, all my values are negative. And as it tracks, we get this nice graph that shows that it's moving in constant speed, constant velocity, and it moves right at -1 meters. So after obtaining this data, I went and designed a computational model using some assumptions that I obtained from this tracker data. So as we can see here, this is the initial velocity and position for the water bottle. So the initial position was right at zeros all across for the x, y, and z component. The initial velocity was obtained right here, negative 0.439 in the x component. That was obtained, if we go back to tracker here, by taking these first two times. And once you take those two time intervals, you can find the initial velocity and use that as a constant track for the rest of it. So that's how we did that. We can go back here. And I also used my delta t at 0.01 so as to have a very small delta t, which allows us to have a much more accurate simulation. Then we can move back here. The net force acting on the object was assumed to be 0. Because according to Newton's first and second laws, if an object is at rest or in constant motion, then the net force acting on that object is 0. So right here, we have Newton's second law just written in code, and also the ball position update formula. So at each time interval, the net force is 0, which means that the ball's velocity will be constant because this whole thing will be 0. And then this ball position update formula allows us, using this constant velocity and our small delta t, to update the ball position at every time increment, which then gives us this nice graph which compares the data both from tracker with our actual simulation and the blue line, which shows our computational model. As you can see, these two lines are extremely close. There's only a little veering off at the edge. This was largely in part of the minimal friction that was ignored in our simulation. This caused the water bottle to slightly slow down near the end of its path. As you can see right here, the velocity gets less steep, which implies that it is smaller in magnitude. In addition to the fact that the water bottle, its size and makeup caused it to be a little bit wobbly, which didn't leave the smoothest track, causing it to, again, not really follow that x-axis and slow down slightly. So now we'll move on, and we will discuss the coordination of the axes. So I decided, again, to have it moving left, causing that to be in the negative x direction, but you can simply flip your axes and you can have the orientation be in any way. So you can choose that moving left is in the positive direction. So if I were to flip my axes, I could then have this graph be flipped to where it is moving up and to the right rather than down and to the right. And lastly, we assumed that the net force acting on the object was zero. And the question is, can this tell us anything about the total pulls and pushes acting on the object? The answer is no. All we know is that the net force is zero and that the forces acting on it cancel out. That means there could be 0, 2, 3, really any number of forces as long as they cancel out on each other. So that's the conclusion of the video, and I enjoy that you guys stick around. Thank you.